In the late 1800s, physics looked like it had nearly finished its job. Scientists had strong laws for motion, heat, electricity, and light. Many believed the remaining work was just clean-up. Measure a few constants more carefully, refine the math, and the world would be fully explained. That confidence shaped everything. When something did not fit, it often looked like a small error, not the start of a new kind of reality. But tiny cracks kept appearing. Certain colors of light from hot objects refused to match prediction. Electricity in gases behaved strangely. Atoms, still debated, seemed to leave fingerprints in experiments that did not follow the old rules. The problem was practical too. Some questions could not be tested yet. Instruments were limited, speeds were too high, distances too small, and effects too faint. Physics had answers, but the universe stopped cooperating. So a different tool gained power. The thought experiment, or Gedanken experiment. Instead of building an impossible machine, a physicist built a situation in the mind, then followed the existing laws step by step to see what they forced to happen. It sounded like philosophy. It became a pressure test for reality. If the logic led to a contradiction, the laws, not the imagination, had to change. That shift opened a new path forward. In 1905, Albert Einstein took the new tool of thought experiments and pushed it until physics cracked. He imagined chasing a beam of light, trying to run alongside it and watch it hang still like a frozen ripple in space. But the known rules did not allow that picture to make sense. Light behaved as if it refused to become stationary for anyone, no matter how fast they moved. That simple mental chase forced a hard choice. Either the old ideas about motion were wrong, or light did not follow the usual rules. Einstein kept two claims and let everything else bend around them. The laws of physics stayed the same for observers moving steadily, and the speed of light stayed the same for all of them too. Those statements sounded harmless. Together, they acted like a trap. Then he shifted to a train passing a platform because speed only mattered compared to someone else. Events that felt simultaneous on the train did not stay simultaneous on the ground. Clocks that rode with the moving observer ticked differently from clocks left behind, and lengths along the direction of motion did not match either. Time and space stopped being fixed backdrops. They became parts of the motion itself. In 1907, Einstein faced a problem that special relativity had not touched. Gravity still sat outside the new rules. He needed a way in, so he used another thought experiment, simple enough to picture in seconds. Imagine an elevator sealed shut. Inside, a person let go of an object. What happened next depended on one thing, whether the elevator accelerated or whether a planet pulled it down. If the elevator stood still on Earth, the object fell to the floor. Nothing surprising. But if the elevator floated in empty space and rockets pushed it upward, the same object still dropped to the floor in exactly the same way. From inside, without windows, there was no test that told the difference. Acceleration mimicked gravity. That idea hit hard. It suggested that gravity was not a separate force after all. Einstein called it the equivalence principle. Locally, feeling gravity and feeling acceleration amounted to the same experience. And once that was true, consequences followed immediately. Light inside the accelerating elevator appeared to bend. Clocks at different heights could not stay perfectly in step. Space and time themselves had to respond to gravity, not just objects moving through them. The elevator did not give equations yet, but it demanded a new theory. By 1915, the elevator idea stopped being just a clever comparison. It demanded a full set of rules for how gravity actually worked. Einstein turned that demand into equations. They treated gravity not as a simple pull, but as a change in the geometry of space and time itself. Matter told space-time how to curve. Curved space-time told matter how to move. It sounded abstract, but it produced numbers. Those numbers made the theory dangerous because they could be checked. One famous test involved Mercury. Its orbit showed a slow twist that older physics could not fully explain. The new equations matched the missing amount. That was a warning sign that something real had been captured. Then came an even stranger prediction. Light should not travel in a perfectly straight line near a massive object. Gravity should bend it. That claim sounded impossible to verify because the sun's glare drowned out nearby stars. The only chance came during a total solar eclipse, when the sun's disk disappeared and starlight could be measured near its edge. In 1919, an expedition led by Arthur Eddington compared star positions during the eclipse with their usual positions. The stars appeared slightly shifted, just as predicted. The elevator logic earned credibility. In the 1920s, physics faced a new kind of trouble. Light and matter refused to pick a single identity. In some tests, they acted like particles hitting a screen in sharp, countable impacts. In others, they acted like waves, spreading out and forming interference patterns. Thought experiments now did real work here. They tested the rules of observation itself, not just the objects being observed. The most unsettling idea was that measuring did not simply reveal an answer, it helped create one. If an experiment was arranged to detect which path a particle took, the wave-like pattern disappeared. If the setup allowed paths to remain unknown, interference returned. The dilemma sounded almost philosophical, but it pushed physicists toward hard structure. A theory that depended on how questions were asked needed a new kind of language. That language arrived as mathematics, built quickly and in parallel. Werner Heisenberg developed matrix mechanics, a method that tracked observable quantities directly, even when picturing a particle's path failed. Erwin Schrödinger developed wave mechanics, describing a system as a spreading wave that evolved smoothly over time. They looked different, yet matched in their predictions. Quantum theory now had two engines, thought experiments to expose the paradox and equations to calculate the outcome. By 1935, quantum theory worked uncannily well for atoms, but it still carried a sharp, unanswered question. What exactly counted as a measurement? Erwin Schrödinger pushed on that weak point with a thought experiment designed to feel uncomfortable. He tied a microscopic quantum event to an everyday outcome on purpose. If the small thing followed quantum rules, then the big thing had to, too. That was the trap. In Schrödinger's setup, a single random atomic decay triggered a mechanism that decided the fate of a cat sealed away from observation. Quantum math treated the atom as not decayed and decayed at once, a superposition. And if that decay controlled the mechanism, then the entire chain stayed linked. Until the box got opened, the logic forced a shocking statement. The cat ended up both alive and dead in the description. That conclusion was not meant as a cute riddle. It exposed the measurement problem in its hardest form. The equations did not say when a fuzzy superposition turned into one clear outcome, or what physical process drew the line. Was it the act of looking, the interaction with the environment, or something missing in the theory? Schrödinger's cat made one point unavoidable. Quantum weirdness did not politely stop at atoms. In 1935, the quantum world looked strange enough. Then it got sharper. Einstein joined with two younger collaborators, Boris Podolsky and Nathan Rosen, and they aimed at the heart of the theory. Their question sounded simple. Did quantum mechanics give a complete description of reality, or did it leave something out? This was not about taste or wording. It was about whether the theory told the full story of what existed. They built a thought experiment around a pair of linked particles. The math said the pair could share one combined state, even when separated. Measure one, and the prediction for the other snapped into place. Quantum mechanics handled this easily, but EPR treated it as a warning sign. If a measurement here let you predict something there without touching it, then that something seemed to have been real all along. So EPR pushed a strict standard. If you could predict a result with certainty without disturbing the system, that result had to correspond to an element of reality. By that rule, quantum mechanics looked incomplete because it refused to assign those definite values in advance. Entanglement stopped being a quirky side effect. It became the pressure point. A single thought experiment turned quantum weirdness into a direct challenge to the theory's claim to be finished. By 1964, the EPR argument still sat in an uncomfortable place. It had raised a challenge, but it had not forced a clean decision. Then a physicist named John Bell stepped in with a different instinct. He treated the debate like something physics could settle, not just discuss. He asked a hard question. If the world really obeyed those comforting local explanations, what exact pattern had to appear in measurements? Bell took the fuzzy words and turned them into math. He wrote inequalities, number limits, that any theory built from local hidden variables had to obey. They were not complicated because he wanted elegance. They were strict because he wanted leverage. If experiments measured pairs of entangled particles and the results crossed Bell's limits, then the EPR style escape hatch failed. It became a simple fork, either locality or something deeper about reality. That move changed everything. A thought experiment stopped being a talking point and became a prediction with a scoreboard. Bell's inequalities did not tell scientists what the universe had to be. They told them what it could not be if the numbers came out wrong. And now the path was clear. Build an experiment that compared correlations in different measurement settings. Check the totals. If the inequality broke, nature had spoken. In the 1970s, Bell's inequalities stopped being a paper test and became a lab target. The basic idea sounded simple. Create pairs of particles that shared entanglement. Measure each one far apart and compare the results. If nature followed local hidden rules, the numbers stayed under Bell's limit. But early experiments kept crossing it. Again and again, the correlations came out too strong for any local explanation. Skeptics did not give up because real experiments had real escape hatches. Maybe the detectors missed too many events. Maybe the measurement settings were not changed fast enough. Maybe the two sides could still influence each other in some unnoticed way. So the tests evolved. Researchers sped up the choice of settings, increased separation, improved detectors, and tightened timing. Each improvement removed a loophole, and the violation still remained. By the 2010s, loophole closing runs combined high detection efficiency with strict separation and fast, unpredictable choices of what to measure. The aim was not to get a dramatic result, but to leave no easy excuse. The outcome stayed the same. Bell's inequalities were violated under conditions built to block local hidden variables. Entanglement no longer looked like a philosophical discomfort. It behaved like a reliable feature of the physical world. By the time the tests kept agreeing with entanglement, the question shifted. It no longer asked whether the effect existed. It asked what it could do. The same setups once used as arguments on paper became routines in real labs, creating linked particles on demand, sending them apart, and checking their shared outcomes. What began as a way to think past experimental limits became something engineers could repeatedly build. That change opened a new kind of technology. In quantum computing, entanglement acted like a special glue between qubits, letting certain problems be tackled in ways ordinary bits never matched. In quantum sensors, entangled states sharpened measurements, pushing timing, navigation, and field detection closer to their limits. None of this required mystical claims. It required control, preparing states, protecting them from noise, and reading them reliably. And the ambition stretched beyond single machines. Quantum networks aimed to distribute entanglement across distance, so separate devices shared a link that could not be copied or quietly intercepted. Researchers chased repeaters, better sources, and longer-lived memories because the physics only mattered if the connections held up outside a perfect setup. The contrast was stark. The old thought experiments filled gaps in what could be tested. The modern ones became blueprints for what got built.